Today, the topic of discussion is on basic concept of strength of materials, that is module 1, part 1, PCME 403. Myself, Dr. Suman Das, HOD, Department of Mechanical Engineering, Swami Vivekananda Institute of Science and Technology. In this chapter, we will discuss deformation in solids, physical and mechanical properties of structural materials, Hooke's law, stress and strain, tension, compression, and shear stresses. An engineer must know the required properties for his products. Various properties of materials may be grouped into number A, that is physical property, and B, that is mechanical properties. Now, physical properties, number 1, that is density, the bulk density or unit weight, that is specific gravity and porosity, permeability and thermal conductivity. Seventh one is thermal resistivity. Next one is the corrosion and the durability and chemical resistivity. Next, the mechanical properties. What are the mechanical properties? Number 1, properties related to axial loading. So that axial loading, that is the load may be tensile load or compressive load. In the case of tensile loading, the strength, that is the tensile strength. So what is tensile strength? If an element is subjected to pulling force, if we pull the element, the resistance developed per unit area is termed as tensile stress, and the maximum tensile stress the material can resist is termed as tensile strength. So to find the resisting forces developed, a section plan may be taken through the element and the equilibrium of any one part may be considered. Each part is in equilibrium under the action of applied forces and internal resisting forces. Now let us discuss this slide. So this is picture A pulling force, that is the P applied on an element, and the section, so that is the picture B, so that is the sigma A, that is the right hand part, and similarly sigma C, if you see that is sigma A and sigma A. So on a particular element, so the total force that on this element, that is sigma into A. Sigma here is the tensile stress. Now it is clearly shown that the figure show the bar under tension and stresses at a cross section, and also an element of bar under tensile stress. So in this P is the tensile force, already I have mentioned. Small p, that is tensile stress, here that is sigma, tensile, that is resistance per unit area, and A is the cross sectional area. Actually tensile stress, that is denoted by the symbol sigma or small p. So finally capital P equals to tensile stress, that is sigma into A. Next, compressive stress. So what is compressive stress? Instead of pulling, if push P act on the element, it tries to shorten the bar, and the internal resistance developed per unit area is called the compressive stress. Just like the tensile stress here, that is instead of pulling, the force is pushing, that is the push force. So sigma equals to, the sigma is the compressive stress, sigma equals to P by A. So finally we are so this is from these three pictures, it is clear about the compressive. Now if the applied force is trying to shear off a particular section of the element, the resistance developed for unit area in such case along the section is called the shearing stress. The maximum stress that the material can resist is called the shearing strength of the material. So this picture clears the view. So here the Q is the shearing force. If the Q is the shear force, so tau is the shear stress, then the equilibrium condition of any part considered shows that is Q equals to tau A, where A is the cross-sectional area of the bolt and tau equals to shear stress. That is Q by A. The next one is properties related to torsional moment. A member is said to be in torsion when it is subjected to a moment about its axis. The effect of torsional member is to twist it, and hence a torsional moment is also called the twisting moment. So in this diagram, that is the torsional moment, or that is called torque. Here torque is denoted by the symbol T. Next, property is related to bending. So in this diagram, there are different point loads are applied on a beam. So this is the bending and bending moment and shear force in the diagram B. Now in the case of resistance to shear, so there are two arrows. One arrow will be up and another arrow will be down. That is the shear force. So resistance of bending, so if you see the diagram that is the figure D, so the middle line that is called the neutral layer or neutral axis, and due to the bending of the beam, the above the neutral layer the beam is subjected to compression, and below that neutral layer the beam is subjected to tension if the moment is as shown in the figure D. Now the simple stress and strain. Intensity of resisting force normal to the sectional plane is called the intensity of normal stress. So this is the figure. So figure A, B and C. From the figure A, it is clear that the section plane is cut a member. So figure D, that is the resistance, internal resistance force developed, and there are two arrows. One arrow is the up and another arrows in the left hand side. And from the figure C, it is clear that sigma is the direct stress and tau is the shear stress. Now intensity of stress is called the simply stress. So mathematically we can express that. So sigma equals to limit del r by del A and finally dr by dA, where r is the normal resisting force. The intensity of resisting force parallel to the sectional plane is called the shearing stress. So shear stress can be defined as tau equals to dq by dA, where q is the shearing resistance. Now in this diagram, it is the variation of shear stress near the ends. That means at the two extreme layer, the shear stress they will be. So this is the stress variation of the member at the extreme layer and in the middle layer. And here the sigma is called the average stress. Now next question comes, what is the unit of stress? Unit of stress will be normally Newton per millimeter square. The other other derived units used in practice are kilonewton per millimeter square, Newton per meter square, kilonewton per meter square, or meganewton per meter square. The stress of 1 Newton per meter square is known as Pascal and is represented by Pa. That means Pascal is nothing but Newton per meter square. So this is the conversion. So 1 megapascal equals to 1 Newton per meter square equals to 1 into 10 to the power 6 Newton per 1000 millimeter square, finally 1 Newton per millimeter square. Now, thus 1 megapascal is equal to 1 Newton per millimeter square. In most of the standard code published, unit of stress has been used as megapascal, that is MPa or Newton per millimeter square. Now the axial stress. So if you see the diagram, the axial stress is nothing but the stress is acting in the along its axis. Figure A, the bar subjected to pull. Figure B, that is the resisting force developed. So this is especially for the tensile stress. Now the resisting force acting on the section are shown in the figure. Now since these stress are uniform, so in that case the resisting force is nothing but equals to sigma into A, where A is the cross sectional area and sigma is the stress. Already I mentioned. So P is nothing but sigma by A. So sigma equals to P by A. So under this type of normal stress, the bar is being extended. Such stress which is causing extension of the bar is called the tensile stress. That means the stress, due to the stress, the bar will be extended. A bar subjected to equal forces pushing the bar is shown in the figure. It causes shortening the bar. Such force which are causing shortening are known as compressive force, and corresponding stress is compressive stress. Already I mentioned. So this is the diagram of compressive stress and as well as compressive force. So this is the resistance and the for equilibrium. So sigma will be nothing but, so in that case P is the force, R is the resistance. So you can write that P equals to R equals to sigma A. So sigma equals to P by E. Now thus whether it is tensile or compressive, the stress developed in a bar subjected to axial force is equal to the load per unit area. Now strain. The change in length per unit length is known as the linear strain. So this is the linear strain, the change in length by original length. So the strain is defined by the epsilon, so del L by L. So from this diagram it is clear that this is the original length L, so del is the extension. Now the lateral strain may be defined as change in lateral dimension per unit lateral dimension. So lateral strain can be defined as change in lateral dimension by lateral dimension. So here change in lateral dimension, that is B dash minus B by B. So B is the original length, B dash is the change in dimension. So change in dimension should be B dash minus B. Thank you.